Hello, my dear student. I'm Saktwala from Educators. I will be with you in physics for Form 5. Now, welcome again for our discussion for our subtopic of rotation of rigid boats on our subtopic of radius of gyration of a rotation of a rigid body. So today we are going to proceed with our discussion here. But before we proceed, we were supposed to remember where we ended on the last session. On the last session, we tried to discuss about the meaning. It means the introduction of the radius of gyration. And after that, we tried to get the definition of radius of gyration. Finally, we tried to demonstrate the formula that we can apply so as to find the value of the radius of gyration. As we know that there are so many questions that you'll be asked to find the radius of gyration. Finally, we proved that the radius of gyration of a rotation of a rigid body is equals to the root mean square. That is what we tried to discuss on the last session. But for our today session here, we are going to see some examples related with the radius of gyrations for a rotation of a rigid body. As we see that we have our example number 4.8. Now we have our example number 4.8. And our example here is categorized into two Roman, which is Roman A, Roman and also Roman B. But on Roman A, we have we have 5 questions that we could be asked to answer here. So let us read together our question Roman A, so that we can know what will be asked to answer from this question. So our question is said that deduce the radius of gyration K. Deduce the radius of gyration of a rigid body of mass M rotating about a various axes at its following. We are supposed to deduce, it means to prepare the radius of gyration K when a rigid body of mass M trying to rotate about the various axes at its it is following. Now we are supposed to consider this parts here. We have Roman 1 up to Roman 5 so as to reduce the radius of gyration. That is what we have been asked on our question. So on Roman 1 here, let us deduce the radius of gyration for the uniform load with the axis passing through the center. Now imagine we are going to see the uniform load. When we talk about the uniform load, this is like the meter rule. That we have the meter rule, and that meter rule having the axis of rotation that is passing through the center. Sasa tunakuwa na rula yetu, ile rula inajaribu kuzunguka at the center. Now, how can we get the radius of gyration? That is what we have been asked on Roman 1. But on Roman B here, on Roman 2, we are supposed to reduce the moment of inertia. It means the radius of gyration for the radius of gyration for the uniform load where with the axis passing at one end. Now we are going to see we have instead if we leave for at the center. Now let us go and look for one end. Now we have the meter rule, and that meter rule having the axis of rotation at one end. It trying to rotate on it is an axis. Now, how can we reduce the moment of inertia? That is what we have been asked on our question here. Roman 3 here, a uniform ring of radius r with the passing with axis passing through its center perpendicular to the plane. Now on Roman 3, we are going, my dear student, to see how can we reduce the radius of gyration for the uniform ring containing the radius r, and also the axis of rotation which is at the center of that ring, and it is perpendicular to the axis of the plane. Imagine we have the ring, we have the ring, and that ring having the axis of rotation. It try to rotate perpendicular. It try to rotate perpendicular to the plane. Now, how can we reduce at the moment the radius of gyration? That is what we have been asked on our question here. But on Roman 4, a uniform disk of radius r with axis passing through its center, center perpendicular to its plane. For the first Roman here, we were supposed to go and reduce the moment of inertia for the uniform disk. Now imagine we have the disk, and that disk having the axis of rotation. It try to rotate perpendicular to the axis. If it rotate perpendicular to the axis through the center, now how can we get the moment? How can we get the radius of gyration for that? The radius of gyration for this uniform disk. This is what we have been asked on our question Roman 4 here. But on Roman 5, we were supposed to assume we have a solid sphere, and this is solid sphere having the radius with axis through its center. Sasa tunaenda kuangalia kwamba tuna solid sphere. Sasa ile solid sphere ina radius r na inajaribu kurotate on it is an axis perpendicular with the plane. Now, how can we demonstrate the radius of gyration? This is what we have been asked on our question here, my dear students. So, and the axis of rotation of this sphere was at the center. Sasa kama radius of the axis of rotation equal at the center, sasa tunapataje ile how can we obtain the radius of gyration? So this is how what we have been asked into our equation. But on Roman B, we were supposed to, my dear student, to identify the radius of gyration of a hollow sphere of mass m and also a radius r about the axis is r. Find the distance of the axis of the center of the sphere. Now imagine on Roman B we have this radius of, we have the hollow, and that hollow sphere containing the radius of gyration and also the mass m, while the radius about the centennial axis is r. Ile axis ambao kwenye ile centennial axis, it means from the point where the axis of rotation started is equal to r. Now how can we get the distance of the axis, the distance of the axis from the center of the sphere? This is what we have been asked in on our equation here. So let us go and see the solutions of these questions from Roman A, starting with the part number 1 up to the part number 5 up to Roman B. So as we observe here, we have our solution Roman A that we have been asked to derive the uniform, it means to derive the radius of gyration for the uniform load when it is trying to rotate where the axis was still at the center of that uniform load. So if we recall our equation number 63 and also 64 and also 18 for our first topic here, the radius of gyration of the uniform load with the axis of the rotation through its center can be expressed by this one. Tumeona tumebandikiwa formula yetu ya kutafuta ile radius of gyration kwenye uniform load. Let us reflect. We know that from the uniform load, the moment, if the axis of rotation is at the center, the moment of inertia is equal to 1 over 12 ml square. But for the radius of gyration, that the radius of gyration must be equals to the length. Kwa kama ile radius of gyration itakuwa ni sawa na length, speed of light ni length, tutaweka radius of gyration na mwisho wa siku tutapata kumbe moment of inertia ni sawa na 1 over 12 times m k square, and we want the k square. Tunataka thamani ya k. Now how can we get the value of k? Now we should say that this k which represent the radius of gyration must be equals here we tried to equate. Tulichokifanya hapa tunachukua ile moment of inertia ambayo ni sawa na mk square pamoja na moment of inertia ambao ni sawa na 1 over 12 m L square. Kwa ukiikweti pale utapata kumbe yule moment yule radius of gyration wa yule uniform load when rotating at the center. When rotating at the center is equal to L times radical of 1 divided by 12.